All right, so let's take a look at some examples of how we would use this and show there are two forms of describing these changes. So let's take a look at the first example I gave you. We have radium-226. So I gave it to you written down as radium-226. But when we do this, you need to write it in this form right here. And then you need to go and find radium on the periodic chart. You have a periodic chart at the back of your textbook. If you don't have an old one, if you kept your chem notes around, or you still have your fancy schmancy little periodic table, you take a look and find radium there, and it is element number 88. And so you put your atomic number up here and your atomic mass down here. And it says it goes through an alpha decay. Now what that means is that you're going to get helium-42 as a particle being kicked out of the radius. Now the thing that we have to remember here is that there is something called the law of conservation of mass, where we state mass is neither created nor destroyed unless you change it to energy, and that's a whole other ballgame. Thanks to Einstein, we got that figured out. But technically, we have to make the numbers add up to the same thing on both sides. Okay? So this is going to be 4 plus some number equals 226. So you subtract this gives you 222. And then 2 plus some number equals 88. So 88 minus 2 is 86. So element number 86 is going to be created here. So we go to the periodic chart and we find that that element is radon. Okay, and so this is one way that you could show this. Another way you can show this although technically this is not completely correct because it doesn't show the balancing there. But when you use the alpha for the alpha particle, it's assumed that that is exactly what you're talking about there. All right, the next example in the script is the beta decay of carbon 14. Now carbon 14 is an extremely important isotope in that a lot of, since we're all organic material, any animal is organic material. If you find something that was alive and has been dead for years and years and years, one of the things we find is that if something is radioactive, as we talked about, the half-lives, the amount of material gets less and less for 50% of each period of time. So if you lose 50% the first period of time, then another 25%, another 12.5%, another 6.25%, and on and on and on like that. Okay? So carbon 14, you could figure out the age or the approximate age by looking at the amount of carbon 14 that is there compared to the amount of carbon 14 that would be there if it were alive. And there is a certain proportion of carbon 14 to carbon 12 that you use for that. But anyway, I digress. Finding the atomic mass here, or atomic number, that's 6. It says it goes through a beta decay, and a beta decay, we use E, and when it decays, it does not change the mass because it's so small of the nucleus, but you will change the atomic number for whatever reason, and I can't really explain that to you. So, to figure out what particles created in this, so what number plus -1 gives you 6, so 6 minus -1 is 7, 14 minus 0 is 14, element number 7 on the periodic chart is nitrogen, and nitrogen 14 is about as stable as you're going to find. it is an extremely stable nucleus. That's the nitrogen we have in the atmosphere that makes up almost 80% of our air. Okay? So that's beta decay. Example number three talks about technetium-95. Now I have technetium-99 in me. I might have a trace of it still, because they use that in medicine for looking at blood flow in hearts, or lack thereof, which is my case. And look at the atomic number for that, that's 43, and we are told it goes through a positron decay. So a positron is the same as a beta decay, except that it's going to have a change of a positive one in the atomic number. Now you don't have to put the plus one there. I'm just putting that down for emphasis as opposed to the beta decay. Plus, then we go 43, what plus 43, or what plus 1 gives you 43, and that's 42, and this is going to stay 95 up here, so we find 42 over here, and we find that that is molybdenum. And we can rewrite this as using a beta instead. I need to do that in the other equation. I'll do that real quick. But this is a positron, so put a B positive there if you want. Plus 95, 42 molybdenum. Okay. Back over here, if we were to fix this one up, we would have 14,6 carbon yields beta negative plus 14,7 nitrogen. Again, this is the preferred one here, but you can use this, or you can put 0, -1 there, and you could put 0 positive one there, but generally this is the preferred method for writing those equations, and that's what I'm going to be, I'll actually be asking for both in the practice problems. The last one is a bombardment problem. And for this one, we're going to be taking beryllium-9, and if you take a look on the chart here, beryllium is element number 4, and we're going to bombard it with an alpha particle. So that means we're going to add to the nucleus of the beryllium helium-42. And it says that you're going to create carbon-12 and a neutron. So the representation for that is C12,6 plus the neutron 10. Now, to make sure that you have it right, everything's got to add to be the same on both sides, both top and bottom. So 9 plus 4 is 13, 12 plus 1 is 13. So the top numbers fit, 4 plus 2 is 6, 6 plus 0 is 6. So this works. Now, another way we can write, all right, so there's another way of showing this, and that is by using the beryllium-94, and then showing the changes going on before and after the bombardment. So we put 2 particles, and this is where we use the symbols. So we put the alpha particle here for the helium, and then we're going to put carbon-12,6 as the main element that's being produced from this bombardment. And then we just have the neutron here. We don't put the numbers with those. We just use their symbols. So alpha and N is what we use for that. And this is basically a shorthand representation of what's going on here. So you bombard with alpha particle, and one of the byproducts is a neutron. Okay? All right. So your practice problems. Any minute now. You are to do these 5 problems here, show how this can be represented in each of the following. Now, for these 2, for this bombardment reaction, in this bombardment reaction, I want to see 2. The one with the regular equation, the one with the parentheses, and the two particles, one bombardment, one byproduct. Okay? Have fun.